So good morning. My name is Danny Latthaus from Delft University, and we are in the charge of work package number 4. And work package number 4 is about accident analysis or demonstrating the safety of the MSFR using all kinds of tools, ranging from analytical tools to full 3D multiphysics systems. So let me, before I dig into the material, state that there have been many contributors to this work package from 7 institutes. It's too many to name them all, but without them, of course, there would have been nothing. So this work package has a number of topics, starting with, well, which transients do we actually have to investigate? Which are the most important ones? Then, because of these, to perform these transients is rather complex, so we need quite a bit of code development in this work package. And because of it's mostly new, it also has to be verified. Then, more on the result side, we have steady state and transient calculations of the MSFR for certain scenarios. And uncertainty quantification is an integral part of looking at these results nowadays. So about relevant transients, so we looked at 2 different classes of transients. The first class involves the fuel circuit, so let's say the reactor core itself, and the second class is related to the emergency draining system. For the first, you could think of loss of heat sink, loss of flow, reactivity insertion, and those kind of things. For the second, it's the draining process of the salt from the core to the tank itself, but also the removal of the decay heat. So like I said, quite a bit of code development had to be done during this project, simply because we have to deal with, well, so much complex physics. So in the neutronics, there's very specifically precursor transports, which is typical for a liquid-fueled reactor. And as far as the fluid mechanics, for instance, we have to deal with turbulence. We have the presence of bubbles sometimes, and of course we have the regular thermal issues. So the aim in this specific task was to build or extend the system that we already have to include these capabilities. Now, what is absolutely necessary to model these systems is, of course, the moving fuel, so moving precursors, 3-dimensionality, especially when comparing to previous EU projects in this molten salt, and of course the most important, feedback effects. So just one slide on some of the code development that has actually been performed. So they're all they have a set of common features in the sense that they are Navier-Stokes-like. Most of them are 3D, precursor transport, as I mentioned. Somewhat more in detail, Polemy and PSI have both used systems based on the open source OpenFOAM, but there are some very specific features here and there, and that is that Polemy has worked on the inclusion of multi-phase flow, so specifically this bubbling process, and PSI has focused more on including effects of the freezing, so the phase change. Then TU Delft has its own in-house codes based on discontinuous finite elements, and the work of EDF and KIT has been based on the Simmer 3 code system. Yeah, so after development of these codes, or redevelopment, let's say, a intercodes benchmarking study has been performed just to see how well we have been doing. And, well, a very special benchmark has been used for this, which was previously developed at CNRS, which specifically targets the molten salt reactor. So it has most of the features that you would normally see in the large MSFR, but now restricted to a, let's say, very simple design. So it's a very simple 2D case, but it contains all of the, let's say, feedback effects that you would normally also have. It has precursor flow, so it's a very good test to look into your codes. Now, the benchmark consists of 3 phases, so starting with something simple like only doing neutronics or only flow, and slowly in different stages you continue to more complex, so fully coupled and even transient. So one One example of such a intercode comparison, let's maybe focus on the bottom part here, which is the fully coupled steady state case. And we look at 3 different code systems with the, in this case is shown the fission rate or the difference with respect to the stationary fluid case. And you see that all of these are very similar. Maybe here you could see it's a bit blocky. That used to be our Delft code system, but that has to do with very specific choices that were made in zoning. Those have now been removed. So all in all, the results are within, let's say, 0.5 to 1% or so. And such a benchmark has been very useful to point out all kinds of problems and issues with these codes and to solve them. So something about the actual transients, and before that, of course, the steady state. You can see here that this is the 1/16th of the core, so one segment. It's a inherently 3D problem. As you see here, the wedge, the core, the heat exchanger, the blanket. Just some results about the steady state. Here the power density as you expect, and the magnitude of the salt velocity, which is not shown here in the heat exchanger because it is a somewhat artificial velocity, we could say, because of all the detail that has been removed. And here you see some of the simulation parameters that were actually used for this system. Now, one example of a CFD calculation of a transient. This is the unprotected loss of heat sink. On the left, the most severe case where we have no heat exchange with the environment at all anymore, and then instantaneous. You see that there's thermal feedback and that the power then decreases to, well, to its decay heat value in the end. So this is still a relatively benign behavior of the reactor core. On the right, a bit more realistic, where the heat exchange does not drop to 0 immediately, but goes more, let's say, gradually, and also not to 0, but to 20% of the original value. So this, let's say, even more benign. Just a last example about transient analysis with a more analytical model in this case. This has to do with the core draining. So how quickly can we actually drain the core? Now, so an analytical model has been built for this, based on macroscopic energy and momentum balances. And the conclusion of this is that depending on the tube diameter which you use to drain the core, you can feasibly drain the core within a few minutes. Yeah, so this is quite a feasible solution. Now the last part of WP4 is uncertainty quantification. Yeah, so the MSFR is very much a multi-physics system. I've highlighted here neutronics and thermohydraulics, but of course there are much more physics involved, chemistry and of course material science, although these are the most, let's say, strongly coupled ones. So indeed, as far as the neutronics, the uncertainties come from nuclear data, and in thermohydraulics, uncertainties come from all kinds of things, because even the modeling in thermohydraulics is less known than in the neutronics. So I've got one example here of a study that was made in this project about uncertainty quantification. This is the MSFR core in the Serpent Monte Carlo code that was used. An uncertainty quantification study completely on neutronics was done by extended generalized perturbation theory. And well, you see here in blue the, let's say, variance of your cross-sectional data of a very specific reaction here. And in red, the sensitivity coefficients of that cross-section to your multiplication factor. And that all then combines into a distribution of your multiplication factor, where you can see that this is quite wide. And this is specifically for the thorium cross-sections. So if you look at the uncertainties of thorium, you get a range of around 1,000 ppm of differences. So this is quite an extensive uncertainty. So this was just an example of the type of uncertainty quantification we have been performing. Then I would like to end with one slide about some of the scientific outputs that we have produced. So directly funded have been 3 PhD theses in this work package. They will be published, I'm sure, around the end of the year. So far, 8 papers and 7 conference proceedings, around 20 master and bachelor thesis projects. So let's say the future of this field. And I'm sure there's much more to come. So thank you.